Welcome to my channel RD Physics. I am Dr. Rashmi Deshpande and this is a course on atomic and molecular physics. This is lecture 7 of the series and today we are going to study the introduction of normal Zeeman effect. So we have seen that when an atom is placed in an external magnetic field B bar, the torque tau acting on the dipole is given by tau is equal to mu cross B. This relation we have obtained earlier when we have studied the interaction between the magnetic moment of the atom and the external magnetic field. So this torque is perpendicular to mu bar and hence it will be perpendicular to L bar also, because we know that the magnetic moment and the orbital angular momentum both are oppositely directed with respect to each other. And because this is a cross product, we know that suppose if a vector is cross product of two vectors, then the resultant will be perpendicular to the plane containing both the vectors. So therefore the torque tau is perpendicular to magnetic moment vector as well as the external magnetic field. So this torque causes precessional motion of L bar about the direction of B bar. This also we have seen how the precessional motion of L bar around B bar takes place, and the angle between L bar and B bar is constant, that is theta remains constant, but L bar is continuously precessing about the direction of B bar. This gives rise to additional potential energy, that is the magnetic potential energy of the atom when it is placed in the external magnetic field, and it is given by the equation Vm is equal to E upon 2m Lb cos theta, where L is magnitude of the orbital angular momentum, B is magnitude of external magnetic field, and theta is the angle between angular momentum and magnetic field. So this expression we have obtained earlier. Okay. The z component of the orbital angular momentum, that is L cos theta, is equal to mlh cross. This also we have seen. So by looking at these two expressions, we can say that the magnetic potential energy Vm is nothing but Eh cross upon 2m multiplied by ml into B. So in the previous expression, we have just substituted for L cos theta. L cos theta, so that is equal to mlh cross, where ml is magnetic quantum number. We have just substituted it. Okay. So this Vm is Eh cross divided by 2m into ml multiplied by B. So what does this show? This shows that in the presence of external magnetic field, energy of a particular atomic state depends upon ml as well as upon n, because we already know that the atomic energy states are dependent upon the the value of the energy state is determined by the principal quantum number n, and this particular expression, that equation number 17, tells us that there is increase in the energy of the atom because of the presence of this magnetic field, and by this much amount each energy state corresponding to every principal quantum number n, the energy will change by this much amount. Okay. So a state of total quantum number n breaks up into several substates when the atom is placed in the magnetic field, and their energies are slightly less or slightly more than the energy of the state in the absence of field. Why less and more? Because we know that ml can take positive as well as negative values. So therefore the energy state will split up. The energy state corresponding to principal quantum number n, it will split up into two 2l plus 1 state, and these energy states will be either more or less than the energy state corresponding to principal quantum number n. So this leads to splitting of spectral lines, because what gives rise to a spectral line? It is the transition between different states which gives rise to a spectral line. Now instead of a single transition now, because in the absence of magnetic field there would have been transition between any two energy levels corresponding to only two principal quantum numbers, say n and n dash. So the transition would have been between energy states corresponding to two principal quantum numbers. But now what is happening? That each state is splitting up into 2l plus 1 level. So therefore there can be transitions between these split up energy levels, and so the number of transitions will be different than in the absence of magnetic field. So the number of spectral lines will also be different than in the absence of magnetic field. So this leads to splitting of spectral lines when the atom radiates in external magnetic field. The spacing of lines depends upon the magnitude of the field. This we can see from here, that because the uh, additional energy level which is appearing here, it is dependent only upon the external magnetic field. It does not depend upon any other thing. This is just a magnetic quantum number. Okay, so which physical quantity determines? The magnetic field determines how much will be the splitting. So therefore the spacing of lines depends upon the magnitude of the field, and this effect is called as Zeeman effect, that is splitting of a spectral line in the presence of external magnetic field is called as Zeeman effect. This is because the scientist Zeeman, who discovered this particular effect, or who observed this effect in 1896, and so after him this particular effect is named as Zeeman effect. So as an example, we are going to consider this example, but let us see how this splitting takes place. So ml can take 2l plus 1 values for a given value of L. So each L state will split up into 2l plus 1 substates in the presence of external magnetic field. These levels are called as Zeeman levels, and ml is called as magnetic quantum number. If you remember, when we introduced this ml, then at that time we have said that this particular quantum number is called as magnetic quantum number, and the reason is simple, that it gives us the splitting of energy levels in the presence of magnetic field. That is why it is called as the magnetic quantum number. So for a hydrogen atom, if we are considering any S state corresponding to any principal quantum number, then S state means L will be equal to 0, and so ml will have only one value, that is equal to 0. So therefore Vm will also be equal to 0, because it is nothing but EH cross upon 2m multiplied by ml into B. So because ml is equal to 0, so Vm is 0. So therefore S state will not split up in the presence of magnetic field. It can be corresponding to any principal quantum number n, but S state will not split up in the presence of external magnetic field. Then what happens for P state? For a P state, L is equal to 1. So ml can take three values, that is -1, 0 and +1. So Vm also will have three values, that is minus EH cross upon 2m multiplied by B, 0, and plus EH cross upon 2m multiplied by B. Okay, so P state splits up into how many levels? 3 levels. D state splits up into 5 levels. Okay, so spacing between any two consecutive magnetic levels. If we want to find out what is the spacing between any two consecutive levels, then we can see from here that each split up state will have this much energy. So ml can change by 1 unit. So therefore eh cross upon 2m multiplied by b, that will be the spacing between any two consecutive magnetic levels or between consecutive Zeeman levels. Okay. Now here, as we have said, we are going to consider this example. What does this diagram show? This is n is equal to 2 energy state which is split up into 3 state. This is p state is shown over here. So for a p state, splitting will be corresponding to ml equal to -1, 0 and +1. So it is split up into 3 levels. And suppose there is a transition from n equal to 3 to n equal to 2. Suppose we are considering a D state corresponding to this n is equal to 3 energy level. Then a D state, as we have seen over here, it will split up into 5 substates. Okay, corresponding to 2, 1, 0, -1 and -2. In the absence of magnetic field, there would have been only a single line corresponding to a transition from n is equal to n is equal to 3 level to n is equal to 2 level. There would have been only a single line. But if there is external magnetic field applied, then what will happen? There can be these number of transition taking place. Of course, these transitions will take place in accordance with the selection rules. What are the selection rules, that we are going to see afterwards, but for time being, just remember that the transitions between different these magnetic levels or Zeeman levels, the selection rules for ML are: the change in ML can be either 0, +1 or -1. Means the magnetic quantum number will not change, or it can change by +-1. These are the selection rules. So following these selection rules, if we draw the different transition lines, then we can see that when the magnetic field is applied, there will be 3 lines instead of just single line. You can see different possible transitions are shown here. Some of them are of equal energy and hence of equal frequency. So here we can see there is a transition from ml equal to 2 to ml equal to 1, ml equal to 1 to ml equal to 1 as well as equal to 0. Then from ml equal to 0 to ml equal to 1, 0, -1. 3 transitions are possible. From -1 to 0 and -1. From -2 to only -1. As I have told you, the selection rules for the change in ml are followed for every transition, and so these are the 9 transitions which are possible. 3 of them means if we are considering this particular transition, ml equal to 2 to ml equal to 1, here the change in the magnetic quantum number is of 1. Okay, there is a change of 1 unit. Similarly here, if you consider this transition ml equal to 1 to ml equal to 0, here also there is a change of 1 unit. And if you consider this 0 to -1, here also there is a change of 1 unit. So these 3 transitions are involving the same energy change, hence they will be of same frequency. So a single line will be corresponding to these 3 transitions. Similarly, for delta ml equal to 0, means for example this 1 to 1, ml1 to ml1, ml0 to ml0, this transition, and ml-1 to -1. This transition, these 3 transitions will also be of the same frequency, and this transition 0 to -1, -1 to this -1 to 0, and -2 to -1. These three transitions also will be of the same frequency. So in all there will be just 3 lines because of these 9 transitions. So in the absence of magnetic field, there is a single line, whereas in the presence of magnetic field, there will be a splitting of this single line into 3 components, which are called as Zeeman components. What is the separation between these consecutive lines, that also we are going to study in detail. We are going to study Zeeman effect in detail. The classical explanation of the Zeeman effect also we are going to study, and we are going to study Zeeman effect in detail afterwards. But for time being, just remember that Zeeman effect is caused because of the applied external magnetic field, strong external magnetic field applied to an atom. And the Zeeman effect, we can say that it confirms the space quantization of orbital angular momentum. Okay, so thank you for patient listening.